Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, today we're going to learn about something about forces in two dimensions, or better known as like the SOHCAHTOA stuff. So if you're looking at, this is mission, forces in two dimension, the key thing is we're going to be working with ramps, and it's really about a little bit of geometry or some shapes. So the shapes are going to matter. And so if I draw a triangle, let me just kind of explain a little bit about this. And so jot this down. If I've got some object on a ramp, a cart, a block of wood, or something like that, so the shapes are going to matter. So if you think about this, there are forces that are acting on this, most notably gravity. But remember, gravity is always pointing downward. So I'm going to draw a line here and call this F grav for the force of gravity. Now, if we know the angle of this, so let's just say for the sake of argument, this is a 22-degree angle or something like that, okay? What other forces? Now, there's a force pushing this down, right? But that's not equal to gravity because of the angle. Also, because it's, let's say, a box on a ramp, there's a force pushing backward called the force of friction, all right? And if you recall, there's also a force pushing up called the normal force. And remember, it's always perpendicular to the contact point, right? We've always done normal forces before, and they've not been at an angle, they've been straight. And so the force of gravity equals the normal force, but it's not going to be equal to the normal force here. And the key to doing these types of problems is really to draw a triangle underneath here. Get a better color here. If I draw a triangle here, essentially the hypotenuse is going to be the force of gravity. All right, and so if we think about this, now this is a, how do I say this? We have like triangles. This triangle, the purple triangle, is similar to this triangle. And so if this is 22, then that makes this 22 degrees. And so if that's 22 degrees, then the normal force is this line, and then the force going downward, this force right here, is this force. Let's call this F1. So this becomes F1, and this right here is essentially it's actually going downward of gravity. So this is, we'll call this F2, but F2 is equal to the normal force, equals to Fn. And so what you'd use is you use SOHCAHTOA to solve for F2, right? If you know this is 22 degrees, and the force of gravity, you know, if let's say we knew the object had a mass of 10 kilograms, so that would be equal like 10 kilograms times 9.8 meters per second, that's 98 newtons, or 980 newtons. So if you know that this hypotenuse is 980 newtons, then you can solve for F2, which is the normal force, and then you can solve for F1, and then you can do problems with this, okay? So that's sort of the big idea. Let's now jump and do some examples. So let's look at example number one. I've sketched out the force body diagram that we had from the question, right? And so this is analytical and no formula. They have a 1.38 kilogram brick. So if this is 1.38 kilogram, let's do the gravity. It's almost always what we want to start with. That's going to be equal to m times g, right? So that's going to equal to 1.38 kilograms times 9.8 meters per second squared. And when you multiply that out, you get 13.5 newtons. So that means that this hypotenuse is 13.5 newtons. And we knew the angle of this, right? It's a 24 degree angle. So this is 24 degrees. That makes this 24 degrees. So then we're going to use SOHCAHTOA. I want to find what this force is. Let's call that F1. I don't know what they call it here and here. Yeah, I call it F1. And we'll call this F2. All right, so for F1, you're going to say, all right, 24 degrees. This is the adjacent angle, right? So I'd say this is 13.5 times the cosine of 24 degrees. And I come out for F1 to be 12.3 newtons. And by the way, what is that also equal to? That's also equal to the normal force, which is 12.3 newtons. Got it? Because F1 is equal to the normal force. All right, let's do F2. F2 is just the same as, same ball idea. It's 13.5, and that'll be times the sine of 24 degrees, and that comes out to 5.4 newtons. Okay, so 5.4 newtons is pushing the block of wood down, and what we need to do is we need to calculate the frictional force, which will be less than the normal force, or the F1 force, and we can find the net force, because the question we're trying to find is what's the net force, and then eventually what's the acceleration. So, right, because the net force on the object, on the ramp, is equal to F1 minus minus FF, right? But we know F1, it's 12.3, so that's easy, 12.3, but I got to find the FF. So remember, the normal force, or pardon me, the frictional force, FF, that's not very clear, is it? The FF is equal to the normal force times mu. And the normal force is 12.3, and the mu is given in the problem as 0.328. So when I multiply those two bad boys together, I get 4.0 newtons. So now, simply what we need to do is it's 12.3 minus all right, that's not 12.3. What did I do wrong? This is not 12.3. This is 5.4. Hold on, F2. That's 13. F2 is 5.4. Yeah. This is not F1. Or pardon me. This is F2. Yeah, F1. There we go. I get that wrong. So this F2 is 5.4. I knew I did something wrong. So 5.4 minus 4 is equal to 1.4 newtons, and that's the net force. Now the question that I often ask, of course, is how fast is the block of wood accelerating down the ramp? Well, then you just plug in F equals ma. Again, I need to throw this pin away. You're going to do F equals ma, and the net force is 1.4 equals, the mass was, I think, 1.3, wasn't it? Yeah, 1.38 kilograms times A. Divide both sides by 1.38 kilograms. That's pretty much close to 1, isn't it? So A, I got on my calculator, is 1.01 meters per second squared. So that's example 1. I know these are complex problems. They take, notice that on the worksheet, you're going to have like whole pages to solve these problems. Let's do example 2. All right, as we look at example 2, the Splash Mountain question. Splash Mountain, Walt Disney's Magic Kingdom in Orlando, Florida. The boats plunge 52 feet down a 43-degree incline. So always start with your diagram, right? So 43-degree diagram. So I've got an angle right here. I'm trying to draw it like it's like 45 or pretty close. And I had to do some thinking about this. I'm going to call this is the 43, which is going to make this 47, because they have to add up to 90, right? So it's actually 47 we're going to work with. And we've got then an object, got it, an object right here. That's the boat or something, Splash Mountain thing. And we're going to draw, first of all, always draw your gravity. So F of G, which we know is mg. All right, then the force coming out of this is the normal force. But then we're going to draw our triangle. Now remember that the gravity is always the hypotenuse. And then we're going to call this force going down. These would be up, straight up. This would be like this. That's the normal force. Okay. We'll call this F1. And then the force going downward is F2. Make sense? So the question is what is the acceleration? And we also know that the mass, by the way, equals question mark. The mu we know to be 0.12, and we know the angle. Now I'm going to use the angle, the degree, at 47. Even though this is 43, I'm interpreting this as that this is the 43. That makes this 47. So we're going to use 47 degrees because that makes this angle here 47 degrees. And I like to work with that top angle. I think it's easier. Okay? Now, you say in the last problem, Mr. Bergmann, we had M. And now we don't have M. So how do we do this? Trust me, it's all going to work out at the end if we do it this way. The M is going to eventually cancel, so it won't matter. So this is just going to be equal to 9.8 M. Okay, so trust me on this. I need to find F1, which is also equal to the normal force. So F1, which equals to the normal force, is equal to, now that's the adjacent of the 47. So I'll say 9, so that means that this is 9.8 M. So this will be 9.8 M times adjacent, that'll be cosine of 47. So you take cosine of 47 times 9.8, what do I get here? I get 6.68 M. We still don't know what M is, okay, that's okay. To find F2, that's going to be equal to 9.8 M sine of 47, and that is, according to my calculator, 7.17 M newtons, because well, this is newtons. It's not, the M is like the mass, like 10 kilograms or something like that. If you want, put a number in it. It'll all cancel out. All right, so we got this F2. So remember, F2 is the force pushing down. So this is 7.17. But the force pushing back here is not F1, it's, or something like that, it's the frictional force. So remember the net force, which is F2, or the force pushing downward, minus the frictional force is the net force. So F net is F2 minus FF, but I have to find FF, so let's do that. The frictional force, if you recall, is just the normal force times mu. The normal force we knew from over here was 6.68 M. 6.68 times M times U. We know U to be 0.12, and that comes out to be 0.80 M newtons, where M is still the mass of the object. So the net force, right, is going to be F2, 7.17 M minus 0.80 M. We can leave our M's together, and I get 6.37 M. Okay, so the net force is 6.37 times M measured in newtons. So now what I'm going to do is I want to find the acceleration. The acceleration, F equals ma. So the F, the total net force, is 6.37 times M, and that's equal to ma. Do you now see what's happening here? The M and the A, or the M's, cancel. And so A turns out to be 6.37 meters per second squared. Because the M's, the kilograms, cancel. So actually in these problems, and that makes sense if you think about it, the M's don't matter. In the previous problem, we had the M and we did all the math with the M, but the M's ultimately cancel when you're doing the acceleration because, as you know, when I drop an object, it doesn't matter, right? It's all going to, if I drop the pen, it's going to accelerate the same as if I drop my phone because, careful, because it is, gravity doesn't, is a no respecter of mass, right? And so it doesn't matter what the mass of the object is, it's going to fall at the same rate, et cetera. Now, the mass does matter to some degree because it does apply to the frictional force. The heavier the mass, the greater the frictional force. So that did play a role here, but ultimately when you're doing the acceleration, it cancels out. So that's it. Forces in 2 dimensions, it's all about playing geometric games, making the triangle, making sure that you realize you always start with gravity, and that's the hypotenuse of your triangle. Then you do a little similar triangle game, and you solve the problem. Houston, we don't have a problem.